linked lists. How is this fundamentally different from the array approach?
The core difference with linked lists is that the items in the list aren't required to be stored next to each other in the computer's memory. Imagine instead of a row of adjacent boxes, you have individual boxes scattered all around a room.
Okay, scattered. So if they're not physically next to each other, how does the computer possibly know the order of the items in the list? How does it know which box comes after which?
That's the absolute key difference. In an array, the order is implied by their physical position.
Yeah.
This box is after that box. But in a linked list, each item, each box, has to explicitly tell you where the next item is located.
How does it tell you?
It does this by holding the memory address. Think of it as an arrow, or maybe a little note with directions, or a signpost that points directly to the next item in this sequence, wherever it might be in memory. So the first box has a note inside saying the next box is over there at address 1234. The box at 1234 has a note saying the next one is at address 5678, and so on.
So instead of relying on their physical neighbors, they have explicit links connecting them together, even if they're far apart in memory.
Exactly. That's why they're called linked lists.
Okay. Our source has this conceptual comparison using alphabetizing student names. How does this illustrate the difference between arrays and linked lists in practice?
Right. Imagine you have a list of student names, perfectly alphabetized, stored in an array. Now, if a new student named, say, Miller enrolls, and you need to insert their name between Jones and Smith.
Shifting time again.
You got it. In the array, you'd probably have to shift Smith and everyone after them one position down to make space for Miller. But with a linked list, you could just create a new node for Miller. Think of it as a new index card with Miller written on it and space for 2 pointers.
Okay.
Then you just find the Jones card, change its next pointer to point to the new Miller card, and then you set the Miller card's next pointer to point to the Smith card. You just reroute the links. No massive reshuffling of all the later names needed.
That does sound much more flexible for adding and removing items, especially in the middle. The source then presents a table highlighting some of these key differences. Let's maybe walk through a few of those points.
Yeah, the table is helpful. It emphasizes that arrays typically store items all of the same type, like all numbers or all strings, and they sit in one continuous block of memory. Linked lists, on the other hand, are made up of these nodes.
Right, the boxes with nodes.
Exactly. And each node contains both the actual data and the address or pointer to the next node. Because they don't need to be contiguous, linked list elements can be scattered anywhere in memory.
Which sounds like it relates to size changes.
It does. This often means arrays are more static or fixed in size. Once created, you allocate a block. Linked lists are inherently dynamic. They can grow or shrink more easily as you add or remove nodes one by one.
Okay. And how do the items in the structure relate to each other in terms of memory? The table mentioned dependency.
Yeah, in an array, each item's location is kind of independent in the sense that it just occupies the next slot in the physical sequence. But in a linked list, an item's place in the logical sequence is entirely dependent on the pointer it receives from the previous item. If that pointer changes, its position in the list changes.
Gotcha.
And finally, the table summarizes what we discussed about operations. Inserting and deleting can be slower in arrays due to that potential shifting, whereas linked lists generally offer more efficient insertion and deletion, especially in the middle, because you're mostly just changing those pointers or links.
Okay, that's a really helpful comparison. Arrays give fast access by index. Linked lists give fast insertion deletion in the middle.
That's the core trade-off, yeah.
Now let's dig deeper into linked lists themselves. The source says each item is stored in a node. What exactly does one of these nodes consist of structurally?
Think of a node as a sort of self-contained little package. It generally has 2 main parts. First, the actual data you want to store, the source calls this the object field. This could be a number, a name, anything.
Okay, the payload.
Right. And second, it has a reference, or what we call a pointer, to the next node in the list that's often called the next field. It holds the memory address of the following node.
So data plus address of the next one.
Exactly, because you can create these individual nodes as you need them. That's the dynamic part we mentioned. And because each one holds the address of the next, a pointer becomes the essential way to keep track of the entire chain of nodes that make up the linked list. The source even shows a simple blueprint, like a little diagram, for a node with these object and next sections.
Okay. And how does the computer know where the linked list even begins? With an array, it's just the start of that memory block, index 0. But if these nodes are scattered?
Excellent question. That's where the head pointer comes in. It's a special pointer, stored separately, that holds the memory address of the very first node in the linked list. Without the head pointer, you'd have no way to find the beginning of the chain. The list would be lost in memory.
So the head is our entry point. And remember that current marker we talked about earlier, the bookmark. How does that work in a linked list?
In a linked list, that current marker is also typically a pointer. It holds the memory address of whichever node we're currently interested in or working with. It's not an index number like in an array, but an actual memory address pointer.
Okay, so head points to the start and current points to our present location within the chain. How do we know when we've reached the end of the linked list? Is there an end pointer?
Not usually an end pointer kept separately, though sometimes there is a tail pointer. But the standard way is simpler. The source explains that the next field of the very last node in the list doesn't point to another valid node's memory address. Instead, it's set to a special value called NULL.
NULL.
Yeah, NEL basically signifies nothing here, or points to nowhere. It's an inaccessible memory address. So when you're traversing the list and you encounter a node whose next pointer is NELL, you know you've reached the end of the sequence. It acts like a stop sign.
Okay, that makes sense. The chain just stops there.
Precisely. The source even includes a diagram, that actual picture-in-memory thing, showing how these nodes can be scattered all over, but they're logically connected by these pointers, forming the list. And it shows the head and current pointers pointing to specific nodes within that scattered arrangement.
Yeah, that diagram is really helpful for visualizing the non-contiguous nature. It's not neat rows like arrays.
Definitely not. It's more like a scavenger hunt, following clues from one place to the next.
Okay. Now, the source goes on to talk about different kinds of linked lists, starting with singly linked lists. What defines a singly linked list? What's single about it?
In a singly linked list, the connections, the pointers between the nodes, only go in one direction forward. Each node in a singly linked list basically has just those two components we mentioned, the data it holds and a link, or next pointer, which is simply the memory address of the next node in the sequence.
Only points forward.
Exactly. Our source gives an example of storing the numbers 23, 54, 78, and 90. Each number sits in its own node. The node with 23 contains a pointer to the node with 54. The 54 node points to the 78 node. The 78 node points to the 90 node, and the 90 node's pointer is NULL.
And the head points to 23.
And the head pointer stores the address of that very first node containing 23, which is your entry point to traverse the entire list, following the next links.
Okay, so you can follow the chain of next pointers to get from the first item to the last, but you can't easily go backwards directly, right? If you're at 78, you don't inherently know that 54 came before it just by looking at the 78 node.
That's the limitation, yes. You'd have to start from the head again to find the node before 78 if you needed it.
Okay, so what are the advantages of using a singly linked list then, if it has that limitation?
Well, the source highlights a couple of main benefits. First, they tend to use a bit less memory compared to some other types of linked lists, because each node only needs to store one pointer, just the one pointing to the next node. Less overhead per node.
Right, only one address to store.
And second, you only need to manage that single set of forward-pointing links when you're doing insertions or deletions, which can sometimes simplify the logic of those operations.
Okay, that sounds like a classic trade-off. Less complexity and perhaps less memory usage, but limited direction of travel. You can only go forward.